Hello and welcome to the Injection Molded Plastic Parts Design Best Practices webinar. My name is Murali Anareddy and I'm joined by my colleague Lotfi Durbil. Both Lotfi and I are Senior Product Managers at Dassault Systems. The goals of this webinar are to provide you with a basic understanding of the injection molding manufacturing process and plastic materials, to share several best practices in the design of injection molded plastic parts, and to learn how you can use a relatively simple and quick injection molding simulation to reinforce these best practices while also avoiding manufacturing defects. In terms of the agenda, we'll start with a quick overview of the plastics materials, moving on to the injection molding manufacturing process. Next, we'll go over several best practices for plastic part design. Then Lotfi will take you through a quick demonstration of how you can use SolidWorks Plastics injection molding simulation software to design better plastic parts. And we hope to have some time left towards the end of the presentation for Q&A. But during throughout the course of the webinar, if you have any questions, there is a questions panel in GoToWebinar that you can use to field your questions to Lotfi and I. We'll do our best to respond to these questions during the webinar, and for those that we are not able to, we'll be sure to get back to you post the webinar. A little bit about ourselves. Again, my name is Murali Anareddy. I have a master's in mechanical engineering from Michigan Tech University. I've been with Dassault Systems similarly for the past 11 and a half years, approaching on 12 years. Prior to that, I was almost 14 years with Moldflow. Throughout my professional career, I was in one way or the other associated with plastics injection molding manufacturing process or simulating the manufacturing process. As I mentioned, I'm joined by my colleague Lotfi Durbil. Lotfi has Bachelor's of Science and Master's of Science in Mechanical Engineering from the University UPMC in Paris. He's been 9+ years with SolidWorks and has a number of years of experience in the fields of structural simulation, fluid simulation, and plastics injection molding simulation. So products and components made of plastics are everywhere around us. We can find plastic parts in the interiors of the vehicles we drive, in our personal electronics, home appliances, and even on a visit to the doctor's office. The global plastics industry has been growing steadily with new applications being introduced into the marketplace every year. And another key growth has been metal to plastic replacement. You know, we see so many metal components being replaced with plastics. So what is behind the popularity of plastics as a material of choice for designers? Well, it's really centered around things like plastics are very lightweight and have very high strength to weight ratio. We can later, as we get into the webinar, you'll see that plastic materials can be highly customized or tailor-made to suit a specific application or a class of applications, and it is for these reasons that designers have great flexibility and confidence that they can achieve the form, fit, and functional requirements by using plastics materials. So whether your application requires say, for example, a specific optical clarity or a certain impact strength or chemical inertness, or your application has to be either electrically inert or electrically conductive, and the list goes on. You can count on that there's going to be a polymer grade that will meet those kinds of requirements. And to their credit, plastics materials manufacturers are constantly innovating, introducing new and improved grades of polymers all the time. They're also working very closely with OEMs in the automotive industry, in the high-tech industry, in the life sciences industries, and so forth, to anticipate tomorrow's requirement and stay ahead of the curve. So it is for all of these reasons that plastics are so popular. And also it helps that for the last 10 years or so, before the current fuel crisis, the prices of gasoline and crude oil and natural gas has been relatively low, which meant the cost of raw polymer, which is sourced from crude oil and natural gas, was also relatively low, and led to a huge adoption curve, if you will. So when we look at plastics materials, you can broadly classify them into two buckets or two categories: thermoplastics and thermosets. And each of these categories have their own unique set of properties and applications. But the primary physical difference between thermoplastics and thermosets is that thermoplastic materials can be remelted back into a liquid, whereas thermoset plastics always remain in a permanent solid state. Think of an analogy that I tend to use is think of thermoplastics as butter. As you know, butter can be melted and cooled multiple times to form various shapes. So that's thermoplastics for you. Whereas, think of thermoset as, say, for example, bread, which, once you've once you've produced bread and it's in its final state, and any additional heat would only lead to either charring or burning up of the bread, but there's really no reusable purpose for that bread. So that's thermosets for you. Now, for the purpose of this webinar, we'll be primarily focusing on thermoplastics polymers. And within thermoplastic polymers, again, you can broadly group those into two categories: amorphous and semi-crystalline materials, thermoplastics. Polymers such as polycarbonate, acrylic, polystyrene, ABS, and PVC. These are all what we call as amorphous materials. And polymers such as high-density polyethylene, polypropylene, nylon would be considered as semi-crystalline materials. So what's the main difference between amorphous and semi-crystalline materials? Well, the main difference between these two classes of thermoplastics has to do with the arrangement of molecular chains and how the arrangement of these molecular chains in turn affects the behavior of the polymer under heat. So in the case of semi-crystalline polymers, they exhibit highly organized and tightly packed molecular chains. And as a result of this, they have a very defined melting point. Semi-crystalline polymers tend to be anisotropic in flow, which means they exhibit greater shrinkage, transfers to the flow direction compared to the flow direction. And because of this anisotropic shrinkage. This can sometimes result in dimensional instability. It can lead to warp, something that as a designer, if you're working with semi-crystalline material, this is something that you'll have to account for, that that the material is going to shrink differently in the flow direction compared to the cross flow direction. Now, semi-crystalline materials have excellent strength and wear properties and good chemical resistance, but they typically lack in things like impact strength. Additionally, the degree of crystallinity can affect many characteristics of the polymer. And they can be varying degrees of crystallinity among different types of semi-crystalline polymers, as well as variations within the same polypropylene. Meaning no two polypropylenes are going to behave the same way. No two polypropylenes will have the same crystallinity structure, and therefore their shrinkage behavior is going to be the same. Whereas semi-crystalline polymers have highly organized and tightly packed molecular chains, the polymer chains for amorphous plastics tend to be more random and intertwined. Think of amorphous polymers, the molecular chains as say pasta, the noodles of pasta. They are sort of unorganized and intertwined and randomly oriented. As a result of this, amorphous polymers have a range of temperatures at which they melt. So they don't have a precise, well-defined melting point. These polymers are isotropic in flow, which means that they shrink uniformly in the direction of flow as well as transverse to the flow. This typically results in lesser shrinkage and less tendency to warp. In terms of the properties, amorphous polymers typically have better impact resistance, but are more prone to stress cracking and poor fatigue resistance. Additionally, polymers that are amorphous polymers have excellent light transmission properties. So if you see a plastic part that is clear, chances are most likely it is made of an amorphous material. Probably a polycarbonate or an acrylic. Now, the next thing that an important thing to consider about materials is things known as additives and fillers. Now, additives and fillers are organic or inorganic compounds that are added to a plastic material in order to give the plastic materials either a specific property or specific set of properties. So most plastics in their original form or neat polymer they have good impact resistance and long-lasting, but they often tend to be very brittle. They can be very hard to work with. They can be easily combustible or too heavy for the intended use. And so by adding fillers and additives, you can transform the plastics so that it meets the intended use without sacrificing the qualities that made the plastic attractive in the first place. And there are, quite a number of additives and fillers that you can choose, each with the each targeting a specific property or deliver a specific benefit. So for example, you have stabilizers. These are chemical additives that inhibit or slow down degradation caused by, say, oxidation or UV exposure or exposure to heat, as well as minimizing reactions with catalysts that can break down the plastic at the molecular level. So by adding stabilizers, you can slow down the degradation of plastic due to these external factors. Plastics, you can also add reinforcements such as short glass fiber to plastics to improve the mechanical properties. And fillers are something that are added to plastics just to reduce the cost and so on and so forth. So as you can see, there's a number of ways in which you can tailor make or customize a polymer to achieve specific design, form, fit, and functional requirements. So why is this all important? Well, I think it's important because different types of plastics have different properties and they all process differently. For example, if we look at some amorphous materials, say like polycarbonate versus acrylic. Now, both of them have excellent optical properties and therefore are good for lens applications. But polycarbonate has better impact strength than acrylic. So how might this play out? So take, for example, a typical car. Both the headlight and tail light lenses nowadays are manufactured using plastic. In the olden days, they were using glass, but nowadays, pretty much all automotive cars use plastic for the head and tail light lamps. Whereas in the case of your headlight lenses, the material of choice tends to be polycarbonate, and that's because polycarbonate, as I mentioned, has excellent impact resistance. And in a car, as you can imagine, the headlight lamps, lenses tend to have lots of objects flying at them, and so the impact resistance is very important. Whereas the same car, when it comes to tail lamps, you would be using, say, for example, an acrylic, because acrylic, they have as good optical properties as polycarbonate, but they're not as high when it comes to impact strength. So within a class of materials, the properties and processability can vary drastically. And I can give you a couple of examples. So in the case of, on the left-hand side, we have polycarbonate. In the case of polycarbonate with a high-flow polycarbonate, if you have a high-flow polycarbonate, you can use it to manufacture, for example, DVDs, which are thin-walled. Whereas if you have a low-flow polycarbonate, you can use it to manufacture, say, for example, bulletproof glass. So you can see that the same class of material can be used to make something as light and thin as a DVD, as well as something that is thick and tough as bulletproof glass. Another example of this is with PVC. In its natural state, PVC is very rigid and therefore perfect for applications such as pipes. Whereas if you were to add a plasticizer, you can end up with a flexible poly PVC, which can then be used to produce things like raincoats. So moving on to the a quick overview of injection molding manufacturing process. There are several manufacturing techniques that are used to manufacture plastic parts. Among them are injection molding, blow molding, extrusion, thermoforming. But for the purpose of this webinar, we'll be primarily focusing on injection molding. There are lots of advantages and benefits to the injection molding manufacturing process. To start with, you can produce very highly complex geometry in what is referred to as net shape, meaning once you inject the plastic into the mold, allow it to cool, and eject the part, the manufactured part that comes out of the mold is ready for use. Often it's very rare that you have to employ secondary operations such as trimming or painting or machining. Injection molding is also typical. It's a process that's it's highly suitable for high volume manufacturing. You're typically talking about hundreds of thousands of parts to millions of parts per year, and all produced out of a single mold. Manufacturing cycle times tend to be very fast. Typically between 3 seconds on the shorter side to up to a minute for thick, chunky parts that are large parts. But generally in the 10 to 60 second cycle. And the manufactured parts themselves typically cost pennies or fractions of a dollar. If you have never seen an injection molding machine, here's what it looks like. Just to give you a quick overview of the functioning of an injection molding machine, think of injection molding machine as two basic components. There's the injection unit on the right-hand side and the mold clamping unit on the left-hand side. The injection unit is where plastic is introduced into the machine. It gets melted and conveyed into the mold. And on the left-hand side, you have the mold clamping unit, which is where the mold is mounted, and the purpose is the machine provides enough clamping force to keep the mold closed during injection. A little bit more detail about the injection molding manufacturing process itself. Plastic pellets are fed into this bucket-like contraption called a feeder. They are then transported into a heating chamber. A combination of heating and friction melts the pellets. And once you have a homogeneous melt of plastic, it is then injected into the mold. And coolant is circulated through the mold to quickly extract the heat from the plastic, allowing the plastic to rapidly cool. And once it is mechanically stiff enough to be ejected, it's ejected from the mold. Some quick injection molding terminology, because we'll be referencing to them during the webinar. The first stage injection, also known as filling phase, is where you're rapidly injecting polymer into the cavity, into the mold. This is very fast, typically under 2 seconds. And once you have the cavity filled, say anywhere between 95 to 99%, you then switch to a holding phase where you're injecting the plastic under a certain specified pressure. The purpose of packing is to compensate for the shrinkage in the material as it goes through a phase change from liquid to solid. Once you have a thing called a gate, and once the gate freezes off, you stop the packing phase. And now at the end of packing, the plastic is still relatively hot. It may not be mechanically stiff enough to be ejected from the mold, and therefore you leave it in the mold for additional seconds to allow it to cool, get to what is called as an ejection temperature, at which point the mold is opened and the parts are ejected from the mold. And as I mentioned, the whole entire process takes anywhere from a few seconds to up to a minute, the whole cycle. So now that we've covered some background on plastic materials and the injection molding manufacturing process itself, let's talk about some best practices for plastic part design. Now, certainly there are many more best practices than we are able to cover today, but what we're focusing on are some basic best practices that, if you follow, will help you in avoiding a lot of the problems that manufacturers incur when they get down to the manufacturing stage. So the number one best practice maintain uniform wall thickness. We will get into more detail on each of these best practices in the coming slides. The second best practice is, follow established guidelines for rib designs, and number 3 is whenever possible, always gauge from thick to thin region, and number 4 is to minimize weld lines. So digging into the first best practice, most plastic parts, regardless of the physical size of the part itself, meaning whether the plastic part, fits into the palm of your hand, or it's the, it's the size of the, or it's the bumper in your car, bumper fascia in your car. The typical characteristic when it comes to thickness is, the thickness tends to be in the range of, 2 to maybe up to 4 millimeters, although 4 millimeters probably is getting on the higher side, or thick chunky section. Now, if you talk about thin-walled plastic parts, you're typically in the 0.5 millimeter range. The minimum limit, or the thinnest that you can go and still be able to manufacture consistent parts with good quality, would be around 0.25 millimeters. Now, I just want to mention that there is a process called as nano injection molding, where the thicknesses can go considerably below the 0.25 millimeter limit, but it's you're dealing with very highly targeted materials, and it's not mainstream. So for the most part, the most injection molded plastic parts that are manufactured, designed, that we come in contact with typically tends to be in these typical thickness ranges. So now the best practice, the first best practice, which is to maintain uniform wall thickness. The reason behind this is it promotes uniform filling and packing. So when your wall thickness is same throughout, and you start injecting the material into the mold, it fills uniformly, and once you get into the packing phase, it shrinks uniformly, and both of these are highly desirable. Maintaining uniform wall thickness will also help you avoid a phenomenon called flow hesitation. When Lotfi gets to his part, and he will show you an example of what flow hesitation looks like in the simulation, and the things that you can do to solve that problem. Maintaining uniform wall thickness also reduces the overall cooling time and achieves uniform cooling across the surface area of the part, and it also helps reduce overall material usage and lower the overall part cost. Now, let's say your design requires a thickness transition from thin to thick. If you look at the graphic on the right-hand side of the slide, there are several ways of achieving this, this design requirement. At the top of the graphic, you have a step change in the thickness going from thin to thick. Right? In this scenario, you will end up with a sharp corner, which is going to result in stress concentration, which can lead to potential premature failure of the part. It can also cause what is called as flow turbulence, which can result in surface defects or cosmetic defects which can show up on the part of the part, on the visible surface of the part. So a little bit of a better design would be to put a chamfer at in the region where there's where you're transitioning from thin to thick. And probably a slightly better design would be to have a more gradual transition from the thin to thick region. However, the best design would be where you're able to core out the thick section and maintain uniform wall thickness. Now, at the bottom of the slide, I have this sort of yeah, schematic of how things influence each other. So if you have uniform wall thickness, it ensures uniform filling, which thereby ensures uniform packing. And when you have uniform packing, it leads to uniform cooling. Uniform cooling will ensure that you have uniform molded in stresses. As you know, most all plastic parts have molded in stresses. These are unavoidable. But when you have uniform molded in stresses, that they result in uniform shrinkage of the material, and which results in minimizing the warpage, the overall warpage of the part. And when you have, and all of this leads to better overall quality of the part. So let's take, for example, this design of a handle. The nominal wall thickness on this handle is 2.5 millimeters. However, as you come around the corner, you can see that we have some sharp corners which result in localized thick sections, which wherein the thickness is no longer 2.5 millimeters, but rather it's more of a 3.5 millimeters. So that means that in these corners, you will have essentially a non-uniform thickness. So the flow, you're going to have the flow of the plastic is going to be affected by this localized thick area. It's going to influence how it packs, and you may end up with some other issues as well. So how would you go about solving that problem? Well, one way to solve that problem is to put add a radii to that section to ensure that you have a uniform wall thickness, and eliminate the potential for localized thick regions and any problems associated with it. The next design best practice is centered around ribs. Now, lots of plastic injection molded parts have rib features in the geometry. Ribs are typically used to add stiffness and strength to the part. Now, when you have ribs, at the base of the rib, where the rib connects to the nominal wall, you have a localized increase in the wall thickness. And this localized increase in the wall thickness can result in a phenomena called sink mark. Basically, what happens is at the base of the rib, you have this thick section, and as this thick section starts to cool down, and if you don't have sufficient material packed into this area during the first and second stage of injection, the plastic will shrink upon itself and basically pull away from the mold surface, and you will end up with a depression or a sink, and this depression will be something that you will be able to see on the opposing surface of the rib. And if it happens to be on, let's say, a visible surface, obviously it's something that's highly undesirable, because it's going to affect the aesthetics of the design. So if we go back to that example of the handle, the same handle that we looked at earlier. Now, let's say we've added some stiffening features, ribs, so in this first design, we have the ribs. The base of the rib is at the same thickness as the nominal wall. So both the base of the rib and the nominal wall are at 2.5 millimeters. And then if you were to use simulation to run, a quick analysis and look at the sync mark result, you can very easily, very quickly see that, you have very significant sync marks, both in terms of their width and in terms of the depth of the sync mark. Now, for the same rib design, if you were to then modify the rib design such that the base of the rib is now, say, 80% of the nominal wall, or 2 millimeters, and if you look at the sync mark result now, it's definitely improved compared to before. Now, probably for the best design would be to use something like, say, 50% of where the base of the rib is 50% thickness as the nominal wall. So in this case, you can see that the sync marks are virtually disappeared. They're no longer going to be a problem. So a quick recap of the rib design guidelines. Rib thickness should be anywhere between 50 to 70% of nominal wall thickness. The height of the rib should be typically between 2.5 times to 3 times the nominal wall thickness. You definitely want to have a draft on the ribs to facilitate smooth ejection from the mold. At the base of the ribs, you want to have a radii, which is 25 to 40% of the nominal wall thickness. And if your design has to have multiple ribs, you want to space them apart such that you're ensuring that there's adequate cooling in between the ribs and you don't have heat concentration and so forth. So the next best practice is gating from thin to, you should always, where possible, you should gate from a thick to thin region. So if you look at the graphic, in the upper left-hand corner, we have the gate location or injection location going into the thin section, which is then transitioning into a thicker section. In this design scenario, you will have problems during both the filling and packing of the mold. That's because the thin section tends to cool off much faster compared to the thick section. And it can often happen that the thin section cools off so rapidly and so prematurely that you're not able to adequately fill and pack the thick section. Now, one way to address this is by adding a localized geometry feature to promote the flow of plastic from the thin to thick section. And this is shown on the right-hand side of the graphic. Although this will partially solve the problem, the flow problem, you're now changing the geometry intent, and you're adding, definitely adding more material to the overall design, and it can also lead to some cooling problems. So a better way to solve this problem is to try and change the gate location, to position the gate such that you're getting into a thicker section if it is possible. Ideally, when it comes to this particular design, perhaps the best scenario would be to try and core out the thick section if possible, such that you have a uniform wall thickness throughout the part. So you don't have this thick, thin region sort of a situation. And the final best practice that we have is to minimize weld lines. Weld lines or nit lines are localized phenomena that are formed when two plastic flow fronts come together. You can see a couple of simple examples. On the example on the left-hand side shows a scenario where you have two gates, meaning the plastic is going to enter the cavity along two flow fronts. At some point, these two flow fronts will come together to create a weld line. Now, you don't need multiple gates for weld lines to occur. If you have a hole in your geometry, or any feature that's going to cause the flow front to split and regroup, you're going to have a weld line, when those flow fronts come together. Now, weld lines are undesirable because they can cause structural weakness. Anytime you have a region of your part with weld lines, it's never going to be as strong as a region without the same weld line. So weld lines can also cause visible cosmetic defects, meaning sometimes you'll be able to see them on, and if it happens to be on a visible surface, obviously that's something that's undesirable. That said, weld lines may be something that are unavoidable. If you have a hole in your geometry and that's a design feature, you are bound to get a weld line one way or the other. So what do you do then? Well, the best practice is to try and minimize the weld lines, and you can do that by trying to use fewer number of gates, and as well as to try and position the gate in such a way that they are formed in non-structural regions, meaning they are they are located in a structurally not critical area. Okay. So at this point of the webinar, we want to introduce simulation software that we call SolidWorks Plastics. SolidWorks Plastics is injection molding simulation software that can help you predict and avoid manufacturing defects. This can help you to eliminate costly mold rework, improve part quality, and decrease time to market. The value proposition is quite simple. We estimate up to 80% of all plastic parts that are manufactured are manufactured using the injection molding manufacturing process. As we quickly reviewed, the injection molding manufacturing process can be quite complex. It's a complex mix of time, temperature, pressure, material, and tooling variables. The injection mold itself can be very expensive, costing anywhere from tens of thousands of dollars to hundreds of thousands of dollars, even across $1 million, meaning mistakes can be very expensive and time-consuming to fix. So the great thing about SolidWorks Plastics is that by using it to early in your design cycle, in a design phase, and avoiding just one mold iteration or design or mold iteration can potentially justify the investment in the software. So with that, let me turn it over to my colleague Lotfi and have him take you through a quick demonstration of SolidWorks Plastics.
Thanks, Murli. So let me. Can you make me presenter?
Okay, how about lunch?
Thank you. So I'm not able, maybe I can. Okay. So I don't know if you can see the right screen because I have not selected the.
So we
which
see
screen? Which one? The SolidWorks?
No, not the SolidWorks, but the other one.
Okay. And now, I think now you can see the SolidWorks one, isn't it?
Yes.
Oh, thank you. So let me provide you a short demo on this sample. So first of all, I would like to show you the workflow that we have with SolidWorks Plastic, and as you can see, we can select a SolidWorks configuration and assign to this configuration, attach to this configuration a plastic injection project. When SolidWorks Plastic is installed, it's Nadine's, and you can see SolidWorks Plastic has its own command manager. So as I start for this demo, a new part, so this is the name, and you can here select the type of process, could be single material, by injection, co-injection, gas assist, and function of the process you select, the following menus will adapt to the right question. And you may select solid or shell. You may use shell for fast filling analysis, okay? Just to test and to take some decision on the design. Let's just start with the default one. As you can see, I have a new tree adapted to the process I have selected. I can decide if I want just to make fill or pack analysis, and then go to through the tree. It's very simple. What I have there is just the ability to select material. I can use the recently used or browse the material database and select from family or from user defined. If you have defined a new your own material, you may select from families, or you may sort by company. And once you have selected, let's say for example a family, just select the right material you want to use. Then all the other settings are proposed by default, and you can now, for example, start by defining the injection location. We have prepared, let's say, a sketched point there. You may deal here with the diameter of the injection location. So for this demo, I'm not using a runner system, okay? But let's say here at the design stage, I have not defined yet the mold layout, so I can start with a simple modelization for the plastic injection. Then we have to create a mesh, okay? So the default mesh usually is good enough. However, here, as we have some fillet, I can select, for example, the curvature base, so that the mesh will be adapted to, to the curvature, like fillet or like rounded shape or something like this. Okay, so just to show you that it's very easy to set up. So it is now meshing. You'll get the pre-visualization of your mesh, and if you are okay, just save it, and that's it. So maybe it's more or less too much. In such case, if you are in pre-design, you want to deal with fast simulation, you can take this cursor and start with the coarser mesh. But for the demo purpose, it's just to show you how to deal with the mesh. So once this mesh is saved, that's it's in process, you are ready to run your first simulation. Okay, so we are not going to do a calculation on live. Okay, and I have prepared some calculated configuration. Okay, let me just once it's ready, select the different configuration. What's the goal here? I would like to check if my part feel or doesn't feel. Okay, that's with the current design, with the selected material, and for some reason we are not using an injection location in the center. So let me start with the original design, exactly this one. Okay, with injection location on this point, like we saw in my previous settings, okay? And I already run this one, and I would like to show you the results of this first simulation. So the part can be filled. That's one thing. Of course, for this, you may look to an advisor, to check if your part is, reliable and so on. You have here an advice. You have a red or green line. You may read, here if you are in a good shape or not with the current process. So, for the purpose of this demo, I would like to show you that we have some defect. First, we have a long well line here, okay? And as well, we have air trap. So on the border, it's not a problem because usually we can, design air vent could be on a parting line or something like this, no problem. But this one is difficult, okay, and could result in a burned area, okay? So let's say for some aesthetical reason, I would like to avoid the air trap on this location. As well, I would like to remove this weld line, and we can understand why. Okay, if we look to the fill pattern, we can see that due to this rip, okay, the flow is accelerated there, okay, and results in weld line there. So, as Murli mentioned, we need, to minimize the thickness. Okay, we need to minimize to have a uniform thickness. But for this part, I need this rip for some reason. Assembly could be structural and so on. So we know that with this weld line, maybe the structure is not good. The stiffness is, we can have some crack for some reason here. So we proposed a new design. Okay, so I'm using a new configuration of SolidWorks where we decrease the thickness of this rib. It results here with the current, fill pattern. Okay, we may guess here that there is still a weld line there. Okay, still because of the thickness of this rib. However, we removed the central air trap. Okay, so that's a good step. We can go further maybe. Okay, and what we are proposing, of course, we need to take into account the constraint of this part. It should keep the function of this part to be assembled in terms of tolerances and so on. Let me go to the third design, and see what happens if I reduce a bit the thickness. Let's display the results. So looks like, due to the red color, looks like we minimized the weld line. Okay, remember we had the long weld line there, which is not good. And about the air trap, we are in a good shape because on the border it's not a problem. By the the mold design by default, this area could be have the right event to remove this air trap. That's the purpose of this first demo. Okay. I don't know if we can go further, but maybe just showing you that we can do some more advanced. So it's not the purpose of this demo, but just want to show you, for example, if you have to, it is, yeah, good. So it's a very simple case where we have an overmolding, okay? So these settings are very easy. Like, for example, you have a multi-body part with SolidWorks, and you just need to assign the different category. For example, here we are assigning to this part metal material, okay, which is steel in this case, the cavity, highlighted in blue, and the runner system. So once you have the multi-body, you'll have automatically this list. The rest is similar to the previous demo. You just need to define the injection location. Here, define it on the at the runner inlet. Sorry, okay, and the results are very easy to interpret. To post results, you are going to see it's like a simple cavity with runner, and combining with the overmolding, you may see here, the melt front, okay, around the the insert, the metal insert. So the overmolding is very easy to set. And through some other results like temperature, like you may let's say if the insert is made with the plastic, you may be interested by the temperature, do some section, see inside, and so on. So like any simulation product with SolidWorks, you are able to deal with the section view, dynamic section view, and so on. And maybe you may check the temperature profile along the contact surface and decide if it is good or not. I think that's enough for today. Okay, maybe we want to, to answer some potential question if you have. So please use the question, the question menu to, and we'll try to answer. Okay. So I can see the first question. Let me see this here. Are we going to get into any time soon? You can also connect. That's not yeah. Okay. So maybe a question for you, Murli.
Yeah, so there's a question about material database, something that I wanted to kind of highlight. Yes, the software comes with an extensive materials database, but more importantly, for the last couple of years, we've been working with the world's leading material manufacturers to ensure that their latest and most up-to-date materials are represented in our database, and we have accurate material data for those material grades. So companies such as SABIC, Covestro, Emscrivery, and many others, we've been working closely with these material supplier partners to ensure that our mutual customers have access to the most latest and complete material data catalogs.
Thanks, Murli. I'm looking to a question concerning the percentage of, I guess, fiber. Okay, the question is how to decide on the percentage of fill and how it affects performances. Okay. Would you like to answer, or?
Yeah, I mean, I can take a shot at it. Typically, the higher the concentration, definitely the the better the mechanical performance, mechanical properties. But that said, there's a trade-off, right? I mean, the higher the concentration, it's going to be more challenging to process the material because the material tends to become more viscous, because of the presence of all the glass fibers, higher concentration of glass fibers. So, a 15% glass fiber versus 35% glass fiber. Obviously, the 15% is going to flow a lot more easier compared to 35%. So there's the processability aspect that you have to consider versus the mechanical properties. Obviously, the 35% is also going to have, as I mentioned earlier, the presence of glass fibers will introduce an anisotropy in the behavior of the plastic. In the flow direction, you'll have one set of properties, typically a lot more stiffer compared to the cross flow, and that difference between the properties in the flow versus transverse tend to exacerbate when you have a higher percentage of glass fibers. So again, 15%, probably the difference in the flow versus cross flow may not be as significant as you have 35%. So these are things that you have to keep in mind. So again, material suppliers are a great resource to talk to as you're considering material A versus material B in terms of which one would be more suitable for your design.
Okay, another question concerning the license of SolidWorks Plastic. So SolidWorks Plastic is an add-on. Okay, so you have to purchase an additional license for SolidWorks Plastic. On existing or on new SolidWorks, you have to purchase it separately. And for the other question, it is not included with SolidWorks Simulation. It's a separate product, okay, that you have to purchase separately as an add-on. So of course, I don't think we have time to answer all the questions, but we'll make sure that we will reply you by email. Maybe we can take one or more question. Murali, what do you think? Do you have one you want to answer?
Actually, I just wanted to briefly mention that there's a white paper that's available for download. So this is it's in the handout section of the GoToWebinar. You will see there's a PDF attached in there. So what the PDF is covering is it's a white paper talking about validation of the software. Validation is a key focus for us because we want to validate the accuracy of the simulation, and we use the insights gained to improve the overall accuracy of the software. And when it comes to validating injection molding simulation software, the best way to go about it is to mold some actual parts and under actual processing conditions, and compare them with simulation. So what we've done is we've partnered with a university in Taiwan to have them as a way that they built 3 different test part geometries, and using molds that have been instrumented with pressure and temperature sensors. They molded up to 125 unique combinations of geometry, material, and process conditions, and generated vast amount of data, which we then used to correlate. So we ran this simulation software for those 125 conditions, and then compared the software versus measured data. And so the white paper captures all of this validation project and the results of the validation projects. It's something that you're able to download and access it from the handout section of the GoToWebinar.
So there is a question about the overmold example that is still on the screen. Okay, so in this case, it's not a multi-injection example. It's overmolding a solid insert, so that there is no flow on both parts. Now, in case you want to simulate multi-injection, yes, you can have 1, 2, or 3, maybe 4 consecutive injection, and we may show the the fill animation of each plastic part. Okay, so hope that it answered the question. The technology behind, so the software is the Dassault Systèmes software after an acquisition. Okay, and the technology is developed by Simulia. Okay, so it is based on the Navier-Stokes equation adapted to the plastic simulation. We may provide you by email maybe additional information. What else? So there are a lot of questions, and I'm not sure we can answer all these questions, but no worries. We have your email address, and I think we may. Any additional answer you want to provide, Nurli?
No, I guess keeping track of time, and we've gone past the hour, so maybe we should just wrap it up.
Yeah, I think so.
Thank you, everyone, for attending this webinar. We quickly gave you a brief introduction to the injection molding manufacturing process, as well as an overview of the injection molding materials, or of plastic materials rather. And then we talked about several best practices for injection molded plastic part design. Things like maintaining uniform wall thickness, following rib design guidelines, where possible, gating into a thick section versus thin section, and minimizing weld lines to ensure that there are no structurally weak areas in your design. So these are all simple best practices that you can follow as you go about designing plastic parts. And of course, a great tool to have is simulation software such as SolidWorks Plastics, to as and when you're making these design modifications or trying out new design ideas, if you want to understand the impact of this design, material processing choices, how it affects the overall manufacturability or the quality of the part. The software simulation software is a great way to go about getting those insight into those questions.